Welcome everyone to this explainer. Today we're going to pull back the digital curtain to reveal the staggering physical infrastructure that actually makes AI possible. We usually experience AI as this magical little chat box on our screens, right? Something weightless and invisible that just sort of lives up in the cloud. But here's the reality. There is no cloud. There are only massive, incredibly heavy, and extremely power-hungry buildings. The physical reality hiding behind your screen is actually one of the most massive industrial transformations of our time.
Okay, let's jump right into our roadmap for today. We're moving from microscopic software shifts all the way to the massive changes hitting your local power grid. We'll cover the rise of AI inference, powering the AI factory, the end of air cooling, the grid under pressure, and finally, protecting your electric bill.
So, Section 1, the rise of AI inference, or as it's sometimes called, moving from the marathon to the sprint. To really get the hardware side of things, we first need to understand a huge software shift that's happening right now.
The crucial point here is that AI is moving from the training phase to the inference phase. Think of training like sending a scholar to a giant library for a year to read absolutely everything ever written. It takes incredible, sustained effort upfront, crunching datasets over weeks to maximize throughput. It's a marathon. But inference, that's you asking that scholar a question and expecting a brilliant answer in half a second. It's continuous, it's sprint-like, and it is hyper-focused on latency because you expect a real-time response.
And get this, because inference runs continuously, 24/7, answering billions of prompts globally, it is projected to consume up to 80 to 90% of an AI system's total lifetime cost. We used to think building the AI, the training part, was the expensive bit. Turns out, just talking to it is what really drains the power grid. Training is just that occasional upfront investment. Inference is the ongoing daily reality, where every single prediction you ask for consumes real power and real compute. But here's where it gets wild. New reasoning models are throwing the old rulebook right out the window. Models like DeepSeek R1 aren't just giving quick answers anymore, they essentially think before they speak. And doing that demands up to 150 times more compute than traditional inference. So, what used to be a quick, lightweight sprint to answer a prompt now requires heavy-duty marathon-level infrastructure just to reason through a single, complex logic problem.
Let's move to Section 2. Powering the AI factory and hitting the physical limits, because the data center itself is evolving from a traditional server room into a heavy-duty industrial factory.
AI compute density is absolutely skyrocketing right now. To push enough power to these clusters at traditional 50-volt levels, the copper cables required would literally be too thick to physically bend or fit inside the server racks. It's a hard physical bottleneck. So the industry has been forced to leap to 800 volts direct current. This is fast becoming the essential architecture to deliver immense power without needing an impossible, rigid mass of copper blocking the hardware.
But honestly, while 800 volts direct current saves space, the primary engineering driver is actually preventing packet loss. When thousands of GPUs are working together on an AI model, they function like a perfectly synchronized orchestra. If the power delivery fluctuates even a tiny bit, data degrades. That's packet loss. One stutter and the whole orchestra falls completely out of rhythm. Pumping higher voltage lets engineers pack these GPUs incredibly close together, ensuring they can coordinate their intense workloads without missing a beat.
Now, this intense concentration of power leads directly to our third section, the end of air cooling and the thermal crisis happening right now in the data center. You know those giant fans blowing cold air across server rooms? Yeah, that's officially dead. It physically just cannot keep up with megawatt-scale power anymore. Instead, direct-to-chip liquid cooling has emerged as the new industry standard. We are literally piping liquid coolants directly onto the silicon processors themselves to pull that extreme heat away from the chips doing all the heavy lifting.
This actually creates an incredible efficiency story around something called PUE, or power usage effectiveness. Traditional data centers using those massive mechanical air chillers hover around a PUE of 1.40 to 1.60. But modern dry-cooled AI factories? They drop that all the way down to near 1.05. How? Well, the chips are so incredibly hot that the liquid cooling them comes back at a scalding 149 degrees Fahrenheit. Because that water is so hot, it can be cooled down just by circulating it outside in the ambient air. No energy-hogging refrigeration required whatsoever.
And this shift doesn't just save millions of dollars in electricity, it's a massive win for water stewardship. Traditional data center cooling towers evaporate millions of gallons of drinking water right into the sky.
But these new chillerless systems operate in closed loops, which means near-zero water evaporation. When you add in the electricity saved from not running giant fans or compressors, a standard 50-megawatt facility can see an estimated $13.2 million in annual power savings. That's huge.
To put this physical footprint into perspective, a single liquid-filled AI server rack now weighs upward of 3,300 pounds. Guys, that's the weight of a mid-sized car packed into a space the size of your kitchen refrigerator. Because of this massive, concentrated weight, standard raised floors in older data centers would literally just crack and collapse under the pressure. Today, facilities require thick, reinforced concrete slabs and earthquake-grade seismic anchoring just to keep these dense machines safely secured.
So we've seen the micro-engineering solutions inside the building. Let's zoom out to the macro impact on your community. Section 4. The grid under pressure. What happens when the AI factory moves to your town?
Here's the thing. When a massive AI facility forces a utility company to build a new power plant or new transmission lines, current regulatory rules often treat them just like any other standard business. And that means the massive capital costs for those grid upgrades are spread across the entire network. In short, your residential electric bill often goes up to subsidize big tech's unprecedented power needs.
But the deeper issue is that AI isn't just power-hungry, it creates massive, instantaneous load swings. Look at your neighborhood's electricity use. It's highly predictable. A slow rise in the morning, a peak in the evening. Utilities plan for this super easily. An AI factory is entirely different. An AI cluster can go from sitting relatively idle to demanding 50 megawatts in the exact fraction of a second a synchronized training job begins. That is literally equivalent to a small city suddenly turning on all its appliances at exactly the same time. Our grid simply wasn't built for these violent, unpredictable multi-megawatt spikes.
So how do we prevent utility bills from ballooning? That brings us to our final section, protecting your electric bill and the fair share approach.
Regulators are actively exploring a fair share playbook right now to handle this transition. Step 1 is accurate demand forecasting, basically preventing utilities from overbuilding infrastructure based purely on AI hype. Step 2 involves large load tariffs, which creates specialized pricing structures so massive energy users actually pay their true cost. Step 3 mandates minimum contract terms, forcing these companies to commit to a region long term. And finally, Step 4 introduces exit fees.
Because without these safeguards, the everyday ratepayer is left holding the bag. Think about it. Imagine a utility builds a massive, multi-million-dollar substation specifically to handle an AI data center. If that tech company goes bankrupt or simply decides to move to a state with cheaper power 3 years later, who pays for that completely abandoned infrastructure? Without strict exit fees enforced by the state, the answer is, you do.
So, I want to leave you with this thought to consider. The next time you ask an AI to write an email or generate an image, how will the incredible, invisible weight of this digital revolution reshape your local infrastructure and your economy? The physical reality of AI is incredibly heavy. It is scalding hot, and it requires a complete overhaul of how we generate and distribute electricity. Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll catch you next time.